Hello everyone, welcome to this video. So in this today's video, we'll be solving the problem number of paths. So this is a medium level question and the company tags are Zoho, Amazon and Microsoft. Okay. And the topic tags are mathematical and algorithms. So once we go through the question, you'll definitely be having this sort of doubt why this is not having the topic tags as DP or maybe some other bottom up approaches or something like that. I'll clarify that thing, but before that let us go through the question first. So the problem is to count all the possible paths from top left to bottom right of an m cross n matrix with the constraints that from each cell you can either move to the right or down. Written answer modulo 10 power 9 plus 7. All right, so m is equal to 3 and n is equal to 3 6. So if you can just see this matrix A, B, C, D, E, F, G, H, I. So we'll even do this, like go through this clearly on the notepad. And if you can just go through the constraints like n goes up to 10 power 8 and m goes up to 10 power 5. So this is one of the reason that we cannot use a DP method or some other brute force technique to solve this. We cannot use any space, we cannot use stack space, etc. So it's very evident that we need to look out for some method that actually doesn't use any sort of space or stack space or even those type of techniques or brute force methods that takes a lot of time. Okay, so we must keep this in consideration. That is the reason we have adopted some other method to solve this question. So there are three concepts here that is involved. Like before that, let us first dry run the example that has been given. M equal to 3 and n equal to 3. All right, and the graph that has been given to us: A, B, C, D, E, F, G, H, I. If I'm not wrong, I'll just, yeah, okay. And this is m equal to 3 and n equal to 3. So you are starting from this point and you need to end at this point. So what are the number of ways that are possible? So A to B, B to C, C to F, F to I. So this is one of the pathway. So I'll write this out here: A, B, C, F, I. All right. Okay, and now we are done with this. And what is another pathway? A to B, B to E, E to H, H to I. All right. So A, B, E, H, I. Okay, and we are even done with the second pathway. Done. And what's another pathway? A to D, D to G, G to H, H to I. So A, D, G, H, I. So we are done with the third pathway. And what's another pathway that's possible? Okay. A to D, D to E, E to H, H to I. So A, D, E, H, I. So this is the fourth pathway. And this is also done. And what are the other two pathways that are left? Okay, did we do this? A, B, E, F, I. No, I don't think so. So A, B, E, E to F, F to I. So we have a freedom of going to down and right, so we can use that. So A, B, E, F, I. Okay, so we are done with 5 paths and there is only one other path that's left out. So what is that? Let me check it from here itself. A, B, C, F, I. Think I have not yeah, I've done. So A, D is over, A, B is over, A, D, E, H, I. Okay, A, D, H, I is also done, and I think A, B, E, F, I. ABEF is also done. So what am I actually left? ABEHI. Okay, AB is also done, and ADEFI, ADGHI, ADEFI, ADGHI. Okay, okay. So okay, this is another pathway that's left. A D, D to E, E to F, F to I. So sorry for a bit of confusion. So A D E F I. All right, so these are 6 pathways that are possible that that can be done, the traversals. So 6 traversals that are possible here, and same is the case with the other thing. This is also self-explanatory. I need not go into the depth. So this is the example, that's given. This is the number of these are the total number of pathways that we need to give as the output. So what is the approach to solve this question? I hope you people understood what are we trying to do. It's the freedom to that is given to us is either you can go down or you can go right. Just use that technique and frame all the pathways possible and return the number of outputs, a number of pathways possible. You need not return the exact pathway. You just need to return the number of outputs, number of pathways. All right. So we are done with this. We understood what are we actually needed to solve, do this like output, give the output. So what is the approach? So I'll divide this question into three concepts. So the first one is combinations. First thing is combination. Second one is modular multiplicative inverse using Fermat's theorem. More precisely for Fermat's little theorem. Okay, Fermat's little theorem. And the last one is binary exponentiation. Okay, binary exponentiation. So this is the thing. So these are the three concepts that we are going to use to solve this question. So now let us clarify regarding these things. Why combinations and how are we actually dealing with combinations? So let us take this example and take the reference. So what is m here? M is equal to 3. So let me don't write this as m or n. It's rows. Rows is equal to 3. And how many columns? Columns is equal to 3. So there are 3 rows and 3 columns. So what can we observe here? To reach the destination from A to I, okay, to reach the destination from A to I, no matter what the path is taken, no matter whatever the path that I'm going to choose, provided that I'm going to use only these two directions, down or right, okay, I'm going either I'll be going to down and right or right and down, that's fine. I'll not be going up or left. Okay, so provided these two, whatever the path that you're going to choose, you'll be using only rows plus columns minus 2 as the total steps. Why is it so? Okay, this has got errors. Total steps. So you can even decode this. So let us take this very first pathway. So A, B, C, F, I. So A to B, one step, B to C, second step. So this is for 2, and C to F, third step, and F to I, fourth step. So totally 4 steps. We are done with this. All right. So we are done with this first pathway. So coming to the second pathway, A, B, E, H, I. First step, second step, third step, and fourth step. So again, we have got 4 steps. So you can even dry run with these 4 pathways, and you can find that there are only 4 steps that we are going to use to reach the pathway. All right. So to reach the final destination. So whatever the pathway you are following, okay. So I'll just write it down here. So whatever the pathway, so independent of pathway, that's much more better. Independent of the path, the total number of steps that are going to be there, that are going to be used is rows plus columns minus 2. So total number of rows plus columns minus 2. So how did we get that? How did we come to rows plus columns and 2? How are we doing it? So because here it is 4, as you can see, whatever the pathway that you're choosing, either this, you'll be ending up with only 4 steps. So that is basically nothing but 3 plus 3 minus 2. Okay, 3 plus 3 is 6, minus 2, that is equal to 4. But how did we come to this relation? So that is basically nothing but, so this is the destination, this is the start, and this is the destination. So for reaching this particular point, you need to travel to the rightmost column, and rightmost column. For traveling to rightmost column, how many steps do you need? Cols minus 1, isn't it? Number of columns minus 1. That's very obvious. This is the rightmost column and this is the beginning most column. So how many steps you need to take? 1, 2. 2 steps, because there are 3 columns here. So 3 minus 1, that is 2. All right. And now coming to this last row, you must travel rows minus 1 steps. Because this is the last row. This is the beginning row. So there are 3 rows that you're traveling. So in total, you must be using rows minus 1 steps. Okay. First step, second step, and here also first step and second step. So totally, you'll be traveling rows minus 1 plus columns minus 1. That is basically nothing but rows plus columns minus 2. All right. So that is the reason we have ended up with this answer. So the total number of steps independent of the pathway, whatever the pathway you're going to choose, provided you'll be only going to the down or left or right. Okay, only down or right. So just a combination of down and right. So the number independent of the path that you're going to take, the total number of steps that you're going to use is rows plus columns minus 2. All right, rows plus column minus 2. So that is the total number of things that you can make use of. Now comes this like the question. So what is the question? Question is all about, you need to find the number of pathways. All right, number of pathways. So let us see this in brief now. I'll just make another thing. So A, B, C, D, E, F, G, H, I. Okay, G, H, I. So in this thing, you can see that. So if I assume these, okay, I'll be using a different thing. So if I say that my down pathways, okay, so it is a combination of my pathway or my path is a combination of X number of downs plus Y number of rights. Okay, D denotes downs, R denotes rights. All right. So if I say my path is a combination of X number of downs and Y number of rights, and I say that this is the particular, these two particular downs is what I'll be using. All right. These two particular downs is what I'm using. What do you mean? From A, I'll be going to D. From F, I'll be going to I. And the rest of the path I'm leaving to you. I'm leaving you to decode what could be the rest of the path. And it's very evident that the rest of the path must be this, what else could be the answer? Or you can even say that from here you can go here, from here you can go here, you can go here. But that is not the case, because I've already told you that I'll be going from I'll be going to I from F. I've already told you that I'll be going to I from F. So in that case, you cannot use this path. You cannot come from H. So this cannot be an answer. This cannot be an answer. So here the thing is, here you're only going to down. You're only going to down, and you're only going to right. It's fine. But what did I ask you? I told that I'll be going to I only from F. I'll be going to D only from A. So you need to construct a path such that you'll be using these two as the down steps, like these two as the down steps, and the remaining things you can construct. And for that reason, I constructed these things. Only this is the possible pathway that I can have. So A to D to E to F to I. So I've told that I'll be using this for sure, this for sure. So this is the only link that I can make. Apart from this, I cannot have any other solution to this. Getting my point? So if you are fixing the number of downs to a particular pathway, okay, I said I'll be fixing A to D path, A to D down, okay, A to D down, and F to I down, okay, F to I down. These are the two downs that I'm going to use, Now I've asked you, find the R's that you need to construct so that you can satisfy this. So what is the R's? There is only one R, D to E, and E to F. This is the only pathway I can construct. Like these are the two R's. Okay, these are the two R's. These are the only things that I can construct. I cannot construct anything else. This is the only pathway that I can have. All right. So what do I understand from this? So if I have the particular number of, I've already, if I fix the D's or if I fix the R's, the rest of the things are also fixed. Okay. If I fix D, if I fix my down pathways, let me write it properly, down pathways, then this actually means that right pathways are also fixed. Okay, right pathways are also fixed. Similarly, if I fix right pathways, then that also means down pathways are also fixed. All right, down pathways are also fixed. So if I use like A to D and F to I is what I wanted to travel, then D to E to F is the only possible solution. There is no other possible thing that you can use of. All right, so this is what it's meant. So but how is this going to be used? How are we trying to use this? So how is this going to be used? This is where the concept of combinations come. Okay, so sorry. So this is where the concept of combinations come. So there are total number of steps that I need to take. Okay, so I'll just use another extra space. So this is the code. So I'll just erase this stuff. Just a moment. So if I say that, so the total number of steps that I need to take is 4. All right, the total number of steps that I need to take is 4. And in that, if I fix the number of downs, number of downs as some x, all right, number of downs as some x. So that dissolves the question, that dissolves that to number of, to find the number of possible ways as 4cx. That's it. Because I know that to reach this particular thing, to reach this from a, from I need to take two down steps anywhere. So I can come from D to E, and then E to H. I can go from A to D, from D to E, from E to F. I can come from then from F to I. So whatever the thing it is, I'll be taking m minus 1, like the columns minus 1, columns minus 1, downs that I'm going to take for sure. That is for sure that I'm going to take. All right, whatever the path it is, I need to come here. That means I need to get down by 2 steps for sure, right? That is very obvious. So for that reason, I know that I'll be going x number of downs. X is basically nothing but cols minus 1. So this is the number of pathways. And what did I explain just before this? That if I fix this, whatever like number of pathways, so let us assume here two col is minus 1, that is 3 minus 1, 2. So there are two downs that I'm going to use. So if I fix like AD is one of the down that I'm going to take, and F5 is one of the down that I need to take, then the other two steps are fixed. And if I say that I need the down is A to D is one down and D to G is another down that I'm going to take, then the rights that I need to do is are also fixed. That is GH and HI. All right. And in this case, AD to FI, DE and EF. All right. So once I fix my downs, the rights are also fixed. So this means this constitute a one pathway. All right. So I just need to find the number of possible downs that is possible. All right. Number of possible downs. So A to D and F to I is one possible down. A to D and D to G is one possible down. And I can also say A to D and E to H is one possible down. So there are various possible. There are 6 possible downs. 6 possible set of downs. Okay. 6 possible set of downs. That is the reason we have got 6 pathways. So once we fix downs, we'll be getting the other 2. That's the rights that we need to do, and we have got one path. Similar is the case, you can even work on rights as well. If I fix number of rights is basically nothing but y. If I assume that is basically rows minus 1. So if I fix that AB and BC is the right that I need to work on. If I say that I'll be going from AB, like A to B and B to C, this is my pakka pathway. This is what I'm going to do, and no matter what, I'll be visiting C from A via B. If I see this, I fix to it, then to reach I, there is only one way. Go to C, F from C and F to I. That's it. CF, FI. These are automatically worked on. These are automatically constructed because there is no other pathway that has been given to you. There is no other choice that is left to you. If you want to reach I, you need to go to F from C, and then you need to reach I from F. That's it. So that is what it is. So if you're trying to fix the rights that you're going to do, downs are automatically fixed. If you are fixing the downs that you need to go, rights are automatically fixed. That is the bottom line of this approach. So now we have got the understanding. So if I need to find this number of pathways, so it's basically turns out to the formula is rows plus columns minus 2 C rows minus 1 or columns minus 1. Both are fine. There is no mistake in it. So rows plus columns plus minus 2 C columns minus 1. Okay, columns minus, both are fine. This is basically simple, right? NCR is basically NC n minus R, right? This is basically this thing only. So rows plus column minus 2 minus of rows minus 1 gives you columns minus 1 itself. So that is the reason these both are equal. So either you go with this, one and the same. All right. Now we are done with this. We have got the formula that we need to use. You can directly substitute rows, you can directly substitute columns and here as well, and you'll be getting the answer, that's for sure. But the trickiest part here is the calculation. Here the n goes up to 10 power 8 and m goes up to 10 power 5. You cannot use this formula directly. That is the reason we need to make use of these two concepts. Modulo multiplicative inverse, that is derived from Fermat's Little theorem, and binary exponentiation. MMI Fermat's Little theorem, this article I'm attaching this link in the description. You can go through that article by Geeks for Geeks itself. It's very explanatory. I cannot put this here because it's very complex, and it even makes our video so lengthy. So I'm skipping this part, but I'm going to explain that. I'm going to tell that formula that we are going to use, and binary exponentiation is what I'm going to explain. All right. So this article I'm putting in the description. All right. I'm putting in the description. So let us erase this part first. So okay, so I'll just take off this. So MMI, so what does that mean? So you people might have seen this formula, A into B modulo M. Okay, A into B modulo M can be written as A modulo M into into B modulo M whole modulo M, right? Whole modulo M. M is the mod. All right, M is the mod, and this is A and B are some numbers. But this does not apply to A by B whole modulo M. This does not apply. Okay, you cannot write like A modulo M and divided by B modulo M and whole modulo M. This is not equal. Okay, these both things are not equal. These both things are not equal. That is the reason we use the formula MMI, that is by Fermat's little theorem. So what does this say? So this is basically nothing but A by B is basically nothing but A into B inverse, right? A into B inverse, that's very evident. A by B is basically nothing but A into B inverse and whole modulo M. So this is basically nothing but A times. So here B inverse of modulo M is basically nothing but binary exponentiation. So I'll write BE, alright, binary exponentiation or power, both are the one of the same. But binary exponentiation is like you can get the power of two numbers very easily and using the bits, alright. So binary exponentiation of B mod minus 2. So we are representing mod here as M, so it is M minus 2. All right, so binary exponentiation of B comma M minus 2, and now you can apply whole mod M. So this turns out to be A modulo M times binary exponentiation of B comma M minus 2 modulo M and whole modulo M. Okay, whole modulo M. That's it. It's very simple. So this is the formula. A times B inverse modulo M is basically A times binary exponentiation of B comma mod minus 2. Alright, mod minus 2. So here we are using M. M is a prime number, that is mod 1e9 plus 7. Alright, that is what we are using. If you are using something else, that applies here as well. So B inverse, so let us assume M is some 11. So you will be writing binary exponentiation and B is some 3. Then this is binary exponentiation of 3 comma M minus 2, that is M minus 2, that is 9. Okay, just apply this. You'll be getting B inverse value. Alright, so this is by modular multiplicative inverse. This is thing. This is derived from Fermat's little theorem. You can watch all the derivations or like understand those things in the through the article, GFG article that I'm putting it in the description. All right, and now this comes up the final thing that has been left out to us is to understand the binary exponentiation. All right, binary exponentiation. So how are we going to do it? So let us take an example. Okay, I'll just erase this path as this point as well. So okay, I'll just take this out, and yes. So let us assume I need to calculate the value of 2 power 13. Alright, let us assume I need to calculate the value of 2 power 13. I'll just minimize this. Let us assume I need to calculate the value of 2 power 13. So if that is the case, what is the binary representation of 13? The binary representation of 13 is basically nothing but 1101. Alright, 1101. So this actually dilutes to, this is 2 power 1101 in terms of binary. So this tells that we have 2 power 8 component and 2 power 4 component, and we have, okay, let me write this properly, 2 power 4 component, and we have 2 power 1 component. That's it. These are the components we have. We do not have 2 power 2 component included here. Alright, so this is the dilution from 2 power 13. We are diluting into 2 power 8 into 2 power 1, 4 into 2 power 1. Now, where do we actually apply the concepts of binary exponentiation? So let us assume, like, we'll just write this out here. So the power that we need to calculate is 13, and the base is 2. Alright, the base is 2. And now let us mention another variable, that is result as 1. Alright, result as 1 initially. Because we have power as 13, alright, because we have power as 13, and 13 is an odd number. Okay, 13 is basically 6 plus 6, or I can write this as 2 times 6 plus 1, right? So we have 2 6 components and we have only single 1 component. Okay, single 1 component. So I can say that if I reduce this power by 2, so power becomes 6, and if I increase the base by twice in the sense not doing like 2 plus 2, like it's because we have divided the power by 2, we will like multiply the base by itself, so base would become 4, and my result my result would be, because I had not included 1, because only 2 times 6 and there's still 1 left, so 2 times 2, that is 2. So if I put these words in clear fashion, 2 power 13 is basically nothing but 2 square whole times 6 into 2, right? This is the thing. So this is basically nothing but 4 times 6, sorry, 4 power 6 into 2, 2 power 13. So this is what I've written. So 6 power is 6, power is 6, base is 4, base is 4, and still the result right now it's there is 2. That's it. And now again divide the power by 2. So this time power is equal to 3, and now base is, because I've divided by 3, the base must be multiplied by itself. So 4 like it's 4 into 4, that is 16, and the result is, and again here 4 power 6 is basically nothing but, I have if I can represent into like 16, so 16 times like 4 square is 16 times 3 into 2, right? 2 power 13. And because there is no component here, there is no odd component here, so I'll just have the result to be 2 itself. And now let us divide the power again. So power is now 1, and base is equal to, because now we have divided the power by 2, base will be multiplied by itself, that is 256, right? 256. And your result would be, because now this 16 cube is basically nothing but 256 whole power 1 into 116 has been left. 16 cube is 16 square into 16 square is 256, and 116 has been left, and into 2, this is basically nothing but 256 times 32. So that is the reason we'll multiply the 16 with 2, that is 32. All right, and now because power, when you divide with by 2 again, it becomes 0. We'll stop this, and whatever the thing that we have, base, will multiply with the result, that is 256 whole into 32. All right, 256 into 32. If you verify this with the calculator, if you want, I'll just put it out here itself. So 2 power so where do you have the power, sorry, 2 power 13 is 8192, and 256 times 32 is also 8192. All right, so we have got the same answer. So once we are just dividing the power by 2, so it's like log of the power. So we are working like that. One, we are distributing it, we are distributing into 2 parts. So power 13 we have distributed into 6 and 6, and only one odd component is left, so that we are multiplying it. So because here, if you can see, the very first thing is left, like 1 2 has been left, that is the reason we are multiplying it the result, and we are getting 2. All right, and here also 116 has been left, 116, this 116 has been left, so that we are multiplying with the result. This is what we are doing, right? 16 into 2, 32, that is what we have got, 32. And finally we are left with base as 256, so 256 into 32, that is 8192. That is the answer. That's it. So this is the concept of binary exponentiation. So we are dividing into 2 parts. If you do not understand this, try to watch this once again, you will get enough clarity for sure. We are just dividing the powers by 2, that is the reason we are multiplying the base by itself. So 2 power 13 is 2 square whole times 6. So 2 square is basically 4. So because we have divided 13 into 6, we must multiply the base by itself. So 2 into 2, 4. That's a very obvious mathematics thing, right? So we are done with binary exponentiation as well. So why did we do binary exponentiation? To evaluate this stuff. B of b comma mod minus 2. All right, so I hope you people understood. Let us go through the code now. So first thing is n equal to rows plus columns minus 2. This is the total steps that we have discussed. Okay, and this can be anything, rows minus 1 or column minus 1, anything. I've just written minimum for just normal sake, it's fine. And for int long I int is equal to I less than r, I plus plus, numerator is this and denominator is this. What do you mean by this? So NCR is basically nothing but n factorial divided by n minus r factorial into r factorial, right? So this is, if you carefully write this is n into n minus 1 into n minus 2 into so on, n minus r minus 1, okay, divided by 1 into 2 into 3 into so on till r, right? Because this and the other n minus r factorial will be cancelled. If you want me to write that again, so I'll just put this out here. Okay, so this is n minus r factorial, right? And here we have n minus r factorial again. So these both will be cancelled, and this is what will be left, n into n minus 1 into n minus 2 into so on, n minus r minus 1 divided by 1 into 2 into 3 into so on till r. All right, so this is like your denominator is increasing till r. This is what it mentions here. I equal to 0, you have 1. I equal to 1, you have 2. I equal to 3 you have like I equal to 2 you have 3. So this is how you are going till I less than r. So I less than r in the sense I equal to r minus 1, and when you add plus 1 to this you have r. So you have framed the denominator 1 into 2 into 3. Same is the case with denominator numerator as well. Numerator starts with n, and in n into, like when it's I equal to 0, you just have n. When it's I equal to 1 you have n minus 1. When it's I equal to 2 you have n minus 2. So numerator is what we are forming. So we have formed the numerator, we have formed the denominator. That's it. I hope you people understood. So this we have converted to this. That's it. And now long log multiplicative modulo multiplicative inverse, that is binary exponent is of denominator modulo mod and comma mod minus 2. So this is, we are making sure we are putting it in the range, and this is a binary exponentiation that we have talked about. So long answer, this is the answer first we'll be having, while exponent is greater than 0. Alright, once exponent is less than or 0, less than or equal to 0, we'll stop this. Less than 0 cannot be formed, get equal to 0. Okay, when it's equal to 0 we'll stop it. So if exponent n1, that is odd, okay, this means odd, okay, this means odd, that is one is thing is remaining. In that case we'll multiply the base that has been there to us with the answer. Alright, so that is what we have done, right? So whatever the answer we have, we'll multiply with that with base. And the next step is base is getting multiplied by itself, and the power is getting divided by 2. This is division divided by 2. That's it. Divide by 2 by right shift. Okay, divide by 2 by right shift, and this is base is getting multiplied by itself. And finally we'll return an answer once the exponent reaches 0. Alright, so this is the binary exponentation concept. Very easy concept, nothing hard. It's very easy. If you try run by yourself, you'll be getting that clarity what are we actually trying to do. And this is also same thing. So the first concept is this is the first concept, this is the second concept, and this is the third concept. So we have learned many concepts. So, and the video will be of course lengthy for this reason, but still I've tried to minimize the stuff by explaining the things very clearly, at the same time maintaining the unnecessary things out of our explanation. All right, so I hope you people understood. If in case you're not able to understand, please rewatch the video once again, you will definitely understand it. So this is numerator times, finally once we get this answer, so we have seen this formula, right? A by B modulo m is basically nothing but A modulo m, or you can even skip this, A times binary exponentiation of B comma mod minus 2 whole modulo m. That is what we are doing here. So this is numerator is A and denominator is B, and that we have done the binary exponential mod minus 2. We have got this value multiplicative inverse, and now we are multiplying these two and divide having the modulo as mod. Modulo mod. All right, so that's it. Very simple thing. Just the calculation and the observation of the combinations thing. I hope you people understood. It's a very good question, to be honest. And let us even submit this for your reference. I think it's not working. Okay. I'll just submit it now and check. It must work because I've tried it already for many times. Just for your reference. Yes, all right, so it's working. So if there are any doubts, feel free to comment in the comment section. I'll definitely revert back to you people. And for your reference, C++, Java, Python codes are also the links of those are also given in the description. You can check them out. And that's it for this video, guys. Please do watch it once again if you have any sort of doubts or something. This is a very good question, must solve question, and a lot of concepts we can learn from this that are especially inclines to competitive programming. All right, so thank you for watching. Stay tuned.